Hi, I'm James Lowe.
And I'm Justine Murphy, and this is Light Matters for June 25th, 2014.
On this week's show, a one-step process produces more efficient solar cells, a two-mode imager better identifies tumors, nanofiber fabrication boosts quantum computing, and we talk with students in a new segment, EDU Spotlight.
A new one-step process for producing efficient anti-reflective materials could mean big things for solar cells. Developed by a team at Rice University, the new process produces black silicon, a material that reflects almost no light. The nanoscale spikes and pores on its surface are smaller than the wavelength of visible light and well suited to solar cells because they allow efficient light collection at any time of day from any angle. The new method for creating black silicon uses a chemical mix of copper nitrate, phosphorus acid, hydrogen fluoride, and water applied to a silicon wafer. This makes copper nanoparticles, which attract electrons from the silicon wafer's surface, oxidize it, and allow hydrogen fluoride to burn pyramid-shaped nanopores into the silicon. This new process could replace an existing two-step method that involves metal deposition and electroless chemical etching. The research was published in the Journal of Materials Chemistry A.
A new technology uses visible and infrared light to pinpoint cancerous tumors in the body, making the process of removing them more effective than with conventional methods. A dual-mode imager developed by a team from the University of Arizona and Washington University in St. Louis combines two systems, near-infrared fluorescence imaging and visible light reflectance imaging, into one package. The near-IR imaging detects marked cancer cells, while visible light imaging identifies contours in the tissue. The new device incorporates a simple aperture filter with a disc-shaped region in the middle that lets in both near-infrared and visible light, as well as a ring-shaped region on the outside that only allows in near-infrared light. Because visible light can't penetrate the outer ring, the visible sensitive part of the filter has a small enough aperture that the depth of field is large. Traditional tumor imaging methods have proven time-consuming and challenging, as additional bulky devices are needed to see near-infrared images and visible light is needed to see the tumor's details. The researchers are now working to develop smaller, lightweight devices such as goggles and handheld instruments for surgeons to use while operating on tumors. The research was published in Optics Letters.
A new approach to fabricating optical nanofibers could enable the next generation of quantum computing. The ultra-high transmission fibers, developed by researchers at the University of Maryland's Joint Quantum Institute, could act as low-power traps for long-lived qubits. To create the new nanofibers, a fine strand of silica fiber is heated by flame to a near melting point and then pulled apart, prompting the middle to thin out until it is about 530 nanometers in diameter. Because the fiber is so small, light can leak out in the form of evanescent waves and trap atoms within a few hundred nanometers. The trapped atoms could then be used as qubits. The researchers are continuing their study, next focusing on interfacing trapped atoms with superconducting circuits. The research is published in AIP Advances.
While we were at Clio 2014 earlier this month, we caught up with a couple of students and asked them about their studies for this week's EDU Spotlight.
What I presented here on Monday was a very high-rate ultra-fast pulse shaper for extremely high-rate analog-to-digital conversion of sparse radio frequency signals using new signal acquisition paradigm called compressed sensing, and I'm going to present the same architecture applied to fast flow imaging.
We're using gold nanoparticles as a way of targeting cancer and killing cancer. So the way we do that is we can tune these nanoparticles, which means that they are bits of gold that are on a rod-like shape, and they're less than 100 nanometers in length, so they're really, really tiny. And we can tune them to absorb anywhere in the visible to the near infrared, depending upon their length to width ratio. So that essentially the longer they are, the more into the near infrared that we can get them to absorb, and the shorter they are, the more we get them to absorb in the blue. And we want them to absorb in the near infrared because actually in the tissue, in the body, it's more optically transparent in that region, and so we get much better depth of penetration. And then we can coat them with antibodies to get them to specifically bind to cancer cells and not to healthy cells. And then so now when we inject the nanoparticles, they will go to the cancer cells and not to the healthy cells. So then when we shine laser light on it, it heats up the cancer, kills the cancer, and then sparing the normal healthy tissue.
Look for more of the EDU Spotlight along with other new segments in the coming weeks.
And that's it for this edition of Light Matters.
Email us with your questions or comments at lightmatters@photonics.com.
Thanks for watching. We'll see you soon.